like introduce basically this webinar in the arrangement of ACRP, challenges for bridges in marine environment. First, a brief introduction of myself. My name is Stavem. I'm the president of the Norwegian Federation for Concrete Repair. Normally, I'm also working as a technical and R&D manager from MAPEI in Nordic and Baltic. This webinar will have 5 parts. First, a bit on ACRP, a bit on marine structures, typically in Norway. Then I will leave the word to Dr. Antonsen for Norwegian bridges in marine environment. Then just a brief introduction on the Marine Structures Working Group, and then questions and comments from the participants. So first I'm going to say some words about ACRP that is hosting this webinar. And this is a non-profit organization founded in 2020. And the focus are activities based on repair, reinforcement, and protection of all kinds of structures and buildings made of different materials, both with steel and concrete. And has a quite close cooperation between the National Association to share activities and to learn. The mission for ACRP is to promote the maintenance of constructions in Europe and to create a European network of professionals and the information, then including all national association, but also companies like contractors, manufacturers, engineers, asset owners, and public administrations, and try to develop the best practice, the regulations, and the trainings that is needed in order to have a good sustainability of the structures we have. So one of the goals for doing this is, of course, to alert the importance of maintenance from in general point of view, to set up and to promote European standards, to promote the maintenance of constructions, both with knowledge and expertise, and how to inspect and to project and execute the maintenance, and try to work within the legislation on regular inspections, qualification on projects, quality control of the systems that are installed, and trying to exchange the techniques and working methods and trainings. ACRP is an open association where both national association can be members, contractors, engineers, and suppliers, and basically all entities involved in this type of specialized activities. The first step of this association was done in 2016 by a common interest for the association STRES and HPHO from Spain, then leading to a joint meeting in Paris in 2019 with 6 countries involved, and then to the establishment of the association in 2020. The important thing for this association is to address some of the important points, that the importance of maintenance, and that maintenance is a part of the life cycle and is not a problem. There is a limited knowledge and expertise in the importance of this thing, and that repair and reinforcement and protection is going together. And you need basically a network working together with both inspection, project, product, and execution. and you need to have standards, regulation, and commitment. And for the main public, it's unknown, and there's basically a need for a specialist. My background and the reason for sitting here today is I'm the president of the Norwegian Association for Concrete Repair. This is a similar association in Norway, established in 1990, and are now holding about 60 different member companies, representing from owner, builder, technical consultants, suppliers, and applicators, and also some personal members. And one of the key aspects in this association has always been that the board should be elected in a way that is representing both all part of the industry, both with the suppliers, but also with the technical consultant and engineers, but also with the owners of the constructions, and with the basically representing the whole business. Also with a quite good cooperation with the Norwegian Concrete Association and a network for young people. The main activities for this association has been, one is to get and arrange a meeting place for all interested parties in this specialized area application. And one of these is to have a conference every year, typically 2 days, with a high focus on different subjects like repair, environment, inspection, new material, but generally organized in a non-scientific way, with approximately 130 people attending every year. The second important part of this association has been the arranging and the training for different courses. One of these is called R for repair, and is a 5-day training covering the national regulation with the safety, calculation, environment, and the EN 1504 series with an exam. And this combined with a training for concrete technology gives you a documented competence in order to do repair and protection of concrete structures. So this is arranged something like 2 to 3 times a year with approximately 60 to 120 people attending. The third activity is the guidelines, and this is also quite important in order to get the written best practice and be able to use this one also for new project. This is a total series about 40 different guidelines based on local conditions, experience, and regulations, and are typically working on areas like ACRP strengthening of concrete structures, with typically the resin-based coating, surface treatment systems, guideline for inspections, guideline for instrumentation and surveillance of concrete structures. Basically trying to put something that is best practice and state-of-the-art for this market. That is short on what the Norwegian Association for Concrete Repair is doing. And in a way of introducing the topic of the day, I'll say something about the marine structures in Norway. Some of the facts of Norway: we have a population about 5.3 million people living there. That is not a really big country in that term. The area is about 385,000 square kilometers. That's about the same size as Germany if you compare. So it's a quite less populated country. What has been important in Norway is the coastline. That in total is something about 101,000 kilometers. And this is actually the second longest coastline in the world, only beaten by Canada. And this coastline has been for many, many hundreds of years and maybe thousands of years been very important for the different industries. And I'll give you some examples, both from the oil and gas industry, some from transport, and also from fish industry. Oil and gas is an industry that started in the North Sea in about 1970 and resulted in the building of some quite large concrete structures from 1975 to 1995. In total, 15 were built, called Condeep. And if you look on the picture here, you will see a little bit on how this one is made and the size. These typical structures, if you take Troll A from 1995 as an example, is about 1.1 million tons of weight. It's a height about 372 meters and are placed on a depth of 303 meters. What is a little bit special on this part in the terms of protection and maintenance is that this one were built with a strategic repair and maintenance philosophy, with a design for concrete with a very low water to cement ratio, with an increased concrete cover, and also, like you see on the photo, using of protective coatings in order to protect. And of course, the obvious reason for doing this is you look on the photo of how to do the repair. You need to do this one by basically climbing, and of course the cost and the way of doing this one is quite difficult. One other example of typical marine structure in Norway is the harbor structures. And quite obviously, this is quite important for both transport and for fish industry. There's several maps showing how many harbor structures there is, but in general, you can see that this one is very, very frequent among the coastline, and there's many, many thousands of harbors. The photo on the top of the right is showing the pier in Trondheim, and with a typical winter exposure. And on the bottom photo, you will see the same pier on the underside. And this is also sort of the issue with this type of structures, is they're very exposed, especially to chlorides, but it's very difficult to do the maintenance, and it's very difficult to actually see if you have a problem with the structure, because then you need to go underneath. And as you see on the photo, this is not really an easy application. And very often you don't really see the problem before it's too late. The third type of structures are the bridge structures that Dr. Antonsen will talk about in just a few minutes. And like with this one, it's quite obviously important for transport and fish industry. For this part, the Norwegian Road Administration has done quite enormous work in order to investigate the bridges and actually understand both the mechanism and basically the exposure. And there's a lot of reports actually showing the microclimate and the exposure on the bridges compared to the exposure of the sea. And I think for this one, I'll give the word over to Dr. Roy Antonsen, and that will speak about the bridges in Norway.
Thank you very much, Paul. And thank you for letting me come to have a presentation here today. As Paul mentioned, I work in the Norwegian Public Roads Administration, and I work within a department where me and my colleagues we are very much hands-on. We go into each of our projects from assessment of the condition assessment of the bridge, and we describe how to repair these bridges, either by concrete repairs, cathodic protection. It can be damages from alkali-silica reactions and so on. So we describe how these rehabilitation is going to be done, and then we also follow up through the whole construction period, and we also finish the projects by its documentation in the end. And sometimes we also follow the rehabilitations after they have been done in order to document the lifetime of the repairs and if we are going to do improvements in the future and how to do repairs and so on. So we are a team working very much hands-on. Now, some of these slides that I made today for this presentation contain some details. We will not have time to go into all the details, but I've included the slides anyway, because sometimes people in the audience like to have a look at the slides after the session is over, and there will be details there giving more information. So I'm going to talk about safer bridges, and quite a lot about safety, and a little less about economic benefits. And also in the end, I will talk a little about climate gases and the benefits of doing rehabilitation. This is Antonsen Bridge, very close to my hometown, and we are starting rehabilitation of this bridge this summer. In fact, it's a process going to take like 2 to 3 years. We are going to strengthen this bridge. Let me start to talk about safety. And this one seems very tough. I'm saying straight out that our inspections are not good enough. Normally, Norway we have very good routines on doing main inspections and documenting the safety of our bridges. But there is one thing that we were never good at, and it's investigating those corrosion within also post-tensioning tendons. Sometimes there will be voids inside the ducts where these post-tension cables are, and we are not very good in examining and documenting this, and I will show you a good example of this furthermore in the presentation. And about cost, I'm saying also here that we save billions by doing maintenance and rehabilitation of concrete bridges. And why? It's because in the 60s, 70s, and 80s, there was a lot of bridges built in Norway, a lot. And these bridges here, they were built with on the other concrete standards, other methods than we have today. In the 60s, 70s, 80s, the standards on the concretes was not very good. And also the concrete cover were typically like 20, 30 millimeters only, and we built in Arctic coastal environments. And of course, there were chloride ingresses. But because there are so many of these bridges built with a poorer standard than today, it's very important to keep them, to rehabilitate them and keep them like alive, because building all these new cross sections or a lot of these new or replacing them by new bridges will be very expensive. And it's not only about money, it's also about the climatic gases that we have to, the emission of climatic gases by producing all these cement and transport processes and all these things. So rehabilitation is extremely important in Norway on concrete and steel bridges. So I will go on, talk about safety. Now this special bridge here, Antonsen Bridge, was going to be I thought in the beginning, this is going to be a simple project. Because I designed a CP system, cathodic protection system for this bridge based on painting, conductive paintings. Because the bridge was like 100% utilized. You can drive a 50-tonner above this bridge, but that's also the limit. Its load carrying capacity is 50 tons, and it was 100% utilized. So I designed a CP system based on conductive paint because it's not heavy, right? So we were going to rehabilitate this bridge, but during the autumn of 2019 we got a surprise. And now I'm going to show you the surprise. Let me just repeat. The purpose was install cathodic protection and also repair the concrete cover because of falling debris. And here is an example of that. Here's like 10 kilos of concrete debris that has actually this concrete cover spalling and loosening and falling down. So it's like 10 kilos falling down in the grass where people are walking under the bridge. Very dangerous. So we had to repair this bridge. But here is our surprise. Cases, once we started doing surface treatment of the bridge because we are going to apply the conductive paint. And it's very normal that we find delamination on coastal bridges in Norway, very normal because of macrocell corrosion, right? But what happened here we never saw before. It's like 100 kilos of concrete that just fell out from this one of the beams in the bridge and revealing revealing also the this steel box here is actually the anchors of the post tension tendons, and they are jointed inside of this steel box. And this I think this box here is called a coupler in English, and it's totally revealed because of the concrete falling out. And what happened here is that we went to see this immediately, and as it happened, and because we have a lot of routine inspecting damages on bridges, and we could see that this delamination here didn't occur recently. It has been there since the bridge was built. The surfaces here are dark and carbonated, and this is old concrete surface, right? So this delamination had been here since the bridge was built, and we also knew that so we suspected something happened when they built the bridge, and it was not recorded properly there in 1966 when it was built. And we also saw that this steel joint here, this joint here is supposed to be grouted. And grouted means that you inject a cementitious mass inside of the ducts and the joints, and this cementitious mass is called grouting, and it's supposed to protect the tendons inside from corrosion, right? And we saw that this joint here was empty. It was not properly injected. So what we do, because of this, we had to get assistance from other people in Statens vegvesen and Norwegian Public Roads Administration. And for those interested of you looking at these names, you can they are all listed here. You can do afterwards if you want. Here is a drawing of the post-stress tendons on the bridge, and for you observant of you in the audience, you can see that these couples, they are here. This is where it was revealed the spalling of the concrete cover in very big amounts. So it was right here. And as I will also mention that this bridge looks like a cantilever bridge, but it's not. It was actually built on formworks in 1966. Also important for me to notify you that Movi has, which is a salmon producer in Norway, they have a very large salmon farm by the bridge, and they do about 40 crossings of heavy traffic every day here, transporting salmon, fresh salmon out to the world, exporting it. So this bridge has a key function for the infrastructure in this society. This is in the coast of North Norway. A key factor there, and was very important for us to examine immediately what about these non-grouted ducts we found, right? And here's the fiber optical analysis. This is within that steel box I showed you there. So this is it's within the steel box there that was not grouted, and this fiber optical inspection showed first only surface rust on the steel wires there, and but it gave us the first concerns that maybe there are other places inside of this bridge where we have voids and empty spaces and corrosion of the tendons. And it's how hard to inspect these tendons, because I will show you later, because here's another one, right? You can see the ducts, and the tendons are inside the ducts that pre-stressed, right? And it's hard to inspect them because these are metallic ducts, and there's only a few methods available which is non-destructive to inspect such voids, right? So but as we went along in the project, we found more and more of these voids there, and and we had to change our plans. So it was no longer like we considered. We had to stop these plans we had about installing cathodic protection, and rather think about strengthening the bridge. But the case is that that we found more and more severe damages, and as you can see here, this is severe corrosion here, gravrust as we call it in Norway, and this you can also see that the tendons here, they are partly enclosed by a very humid mass, and this mass here has been analyzed in laboratory, and it's a mixture of partially injected grouting here, cementitious mass that has been frozen over the years, and very small particles. We only found small traces of chloride and sulfate inside here. But this void that you're looking into here, we have removed the duct here, right? So originally this happened inside of a closed duct, and there was humidity enough there to sustain corrosion, and air enough also. And the corrosion mechanisms happening or going on inside of these ducts are completely different than the ones we are used to on coastal bridges, where you have chloride-induced macrocell corrosion. These are corrosion mechanisms occurring inside there. It's completely different. And we have a collaboration now with the university in Trondheim, and we have master theses being written on these corrosion mechanisms as I'm speaking now. So let's go on. Here is the area has been cleaned from all corrosion deposits, and you can see that the cross-section reduction of these steel wires here is about 1/3. And of course, we started getting afraid. Why should we think that this is like the third, fourth place we opened the bridge, and why should we think we found the worst place, right? We of course, we knew there has to be places even worse, right? And so we kept going in the project. Found this one too. And because the bridge was 100% utilized, we became a bit worried, because there is actually no reduction. There is no margin for reduction on cross sections of the tendons, and there's no margins on lack of interaction between the tension cables and the concrete either. So this group of specialists that was appointed there, they had a hard time by calculating. By doing the calculations, verifying that we were in the safety margin still on this bridge. So the static calculation showed that the bridge had to be strengthened, had to be monitored, and the remaining lifetime was only set to 3 years. And then the Nordland County there that owns the bridge now had to build a new bridge. And this time the Norwegian Public Roads Administration we were too late with the rehabilitation. This time it's because our inspection routines were not good enough. It's usual that we are a bit late rehabilitating bridges, but it's usually because of lack of funding and money. But this time here was because our inspection routines were not good enough. Notice also that the price tag for a new bridge is 220 million NOK, and the rehabilitation project had a budget of 13 million, and this is usual. We normally enhance the lifetime of the bridges when we go in and do full repairs of them. We enhance the lifetime of them like 30 years. And usually for a price tag that is just like 10% of the investment cost for building a new crossing, just 10% to increase the lifetime with like several decades. Very interesting because of the economic benefit of doing rehabilitation, right? So let me talk about the inspection methods. We have the ultrasound, and we have the ground penetrating radar and impact echo. These three combined are good to detect voids within inside of concrete ducts. And here's an example of ultrasound measuring equipment. And this one here is not. There are some units now that you can get that is scanning the surfaces, but not combined scanning with the ground penetrating radar and ultrasonic combined, but you have this scanning equipment available now. I will just show you a video, an example of one measurement he did there, one measurement, and imagine how long time it will take to scan the whole surface of the bridge. It's impossible, right? So it's about, we need new inspection methods, equipment, and all this to We have got the funding in Statens Vegvesen now, Norwegian Public Road Administration, to carry on a project which is called VESPA. And we have the funding now to help develop this kind of equipment, and also to map a lot of other bridges in Norway, and also to establish the routines necessary for inspecting these voids. Notice this one. Here is the Harresund Bridge, and these are different sections that we had to prioritize and measure certain sections of the bridge with respect to voids. And the bridge middle is here, and the length of this bridge middle that was examined is like 2 meters width, and the other sections here are just 1 meter in width. Notice there the red ones here. Those the red ones are missing grouts. So when it says 100%, it's 100% void. There's nothing in there, right? And you can see the midsection here, or was only partially injected in 1966 when it was built, only partially injected. And there you have several areas, other areas here. It's either only partially injected or not injected at all. So it's easy to, we have the equipment. It's not easy. It's very tedious to do this examination. Like only these measurements here took a whole week of work. And I'm not talking about a normal working day. I'm talking about like 12-hour working days for a whole week to get these results. It took a long time also to analyze the results. But they were verified, as I will show you later. The measurements, the conclusions from this work is that the measurements combine the ultrasound and the ground penetrating radar and impact echo together. They are suitable for locating cavities in the ducts. And the methods needs to be developed for faster scanning of lateral surfaces, and all the measurements in the critical section showed varying amount of cavities in Harresund Bridge. And some ducts showed cavities over several meters in length. As this one. This is 6 meters in length here, and you can see that the red areas are totally voids. Very scary results we found there, and therefore when we verified the results, we actually took a 32mm drill and we drilled straight right onto the tendons. We would never do this because we're always afraid of damaging the tendons, but this time we had to verify what our measurement results. And as you can see here, this one here is like a red zone of us. We measured the ultrasound and all these things saying that it was empty, and it was empty. So we verified the measurement methods, and notice also that we did not damage the tendons inside. There's a lot of corrosion in there, and therefore we verified our suspicions on the voids there. Yeah. And Anita, if you can start this. Wait before you start the video. Remember that these are post-tensioned tendons, right? So there's a lot of force on this each of these steel wires. You cannot move them. But what we did here is that we put a screwdriver within you cannot see the screwdriver, but we put a screwdriver in there and we applied some force on these steel wires. We wanted to see if we could move them, and because we were afraid that there were some fractures on them because of corrosion. And now, Anita, you can start the video. And this is what happened. So this one here is broken. Yeah, you just know it's broken. So notice also there are no destructive methods for mapping the extent of corrosion inside. We can measure the voids, right, but not the corrosion. So we had to do a full-scale test on the bridge because we were uncertain about the calculation. So we put a 50-tonner on top of there, and we measured the deflection on the bridge. And this guy under the bridge here is measuring the cracks, the crack width, how it changed before and after we applied this 50 tons pressure on top of the bridge. And all the results were within the expected. So the deflection was like 30 millimeters, and the crack width was just changed like a 1/10 of a millimeter. So we were within the safety margins, but because of the corrosion there, we decided, here you can also see we found later the corrosion cracks, or actually the threads have been totally corroded away. But these are scary photos, but still we were in the safety margin of the bridge, deciding anyway to strengthen it. So here's the carbon fibers that were applied, And for those interested, you can see the details on the design of the strengthening systems. And I will just show you that how we applied the carbon fibers under the beams here. It was glued on with epoxy. So this is a safety precaution for the remaining 3 years of the bridge, and it's but the Nordland County still has to build a new bridge here because of the corrosion ongoing in the main carrying system of the bridge. So what needs to be done now? And the project I mentioned that we have getting financing in the Public Road Administration, what we will do is that we will try to help the market develop these measurement methods. And we have set a time frame on this project like 2 to 3 years. You need to map a lot of bridges and to set some priorities. And luckily in UK, they have done a lot of work on this from before. There's a good standard, and UK standard showing how to help you do priorities for, like we own a lot of bridges, and you can assess a lot of these structures or give you need a priority list on where to start, right? And we estimate that we have to do a condition service of like 300 bridges over the next 10 years with respect to cavities in the ducts, right? And of course, when the Harrison Bridge will be demolished in 3 years, we would of course like to open furthermore places and study the corrosion inside there. We need to understand the mechanisms. For those of you that works with electrochemistry, you saw that the tendons there, they were partly enclosed by this humid mass. And then you also, for those interested in electrochemistry, you would know that there are different options there on how corrosion can occur being only partly enclosed by a mass like this, in humid mass. We also have some suspicions that there might be a corrosion due to what's it called, not embrittlement, but spänningskorrosion. I will maybe spänningskorrosion, it's in Norwegian. I will come back to that. So we need also to keep on doing static calculation and check if it's possible to repair these kind of damages. I will talk a bit about cost also. Now we go straight to cathodic protection, and this is Sortland Bridge in the north, also in Norway. And I usually refer to this one as the crown jewel of cathodic protection in Norway, because it was the first bridge being rehabilitated by this method. And at that time, they did a lot of right things. They were actually excellent. The white fields there on each of these pillars, these are cathodic protection by a titanium mesh and sprayed mortar. This CP system is soon 30 years old. 30 years old, still running, and the values are very good. The only thing that we have started losing on this is the reference electrodes. They are on the end now of their lifetime. And we are going to put the new reference electrodes in there and keep on running. This CP project has been astonishingly successful. There was a lot of corrosion damages on Sortland Bridge, and they only after 7 years of operation. And this bridge here, we can clearly say today that it would not exist today without being cathodically protected. It would not be there. So this is a 30-year-old project. Now I'm going to show you a new one. And this is Breisund Bridge in Lofoten. I suppose a lot of you in the audience have heard about Lofoten. It's a pearl of nature in the north, and a lot of tourists visit this area every year. We were finished rehabilitating this bridge in 2017, completely new and modern cathodic protection system. We are very proud of this one. The reason I show it here is that we calculated this one, Breisund Bridge, and its sister bridge, completely the same design, just 100 meters away here. These two bridges we rehabilitated for like 50 million NOK, and it was also estimated at that time building a new crossing there would be 10 times higher. So we stayed also there within 10% of the investment cost of building new crossings. We take care of these old concrete bridges. This one here was built in '82. And then we have Molde Bridge here, which is the biggest cathodic protection system in Norway. We have like 23,000 square meters of cathodic protection that has been installed here. This project will finish this summer. Also a good example that we are able to protect these bridges and take care of them, even though they were built with bad concrete standards in the 60s and 70s, 80s. It's totally possible to maintain them for decades. And I mentioned also that there are some new technology on the way, the conductive painting, where we also expect to have additional cost reductions on cathodic protection systems in the future. I will also talk a little, I just mentioned the climatic gases. I don't have numbers yet, but we also have established a new project on this. It's simple mathematics, right? We reduce CO2 emissions a lot by rehabilitation. What we're going to do now is we are going to do case studies now on several bridges in Norway. We're going to rehabilitate them, and we are going to make we are going to do all the calculations on how much we save on CO2 emissions by doing rehabilitation. We have been very good in documenting the money saved, but not the CO2 emissions so far. But this will also be taken care of now in the coming years. And for those of you interested in this, you can just contact us in the Public Road Administration. So these numbers will be officially available for anyone. Okay, I think I stop there.